This video is about the Bohr model. Before learning about the atomic model that was developed by Danish physicist Niels Bohr, let's return for a moment to the Rutherford model. The assumptions of this model are that almost all of the atom's mass is contained in a very small dense volume, which we call the nucleus, that all the positive charge in the atom is also contained in this nucleus, and that negatively charged electrons orbit the nucleus in circular orbits. A major problem that Bohr pointed out in the Rutherford model is that electrons in circular orbits have centripetal acceleration, and as a result of accelerating, electrons would emit electromagnetic radiation, lose energy, and eventually spiral into the nucleus. Note that this reasoning is based on the classical theory of electromagnetism. Of course, if electrons would fall into the nucleus, matter as we know it would not exist, so the Rutherford model needed some modifications. So let's see how the Bohr model is an improvement upon the Rutherford model. Keep in mind that the Bohr model was developed based on the hydrogen atom, which contains one proton and one electron. Now the Bohr model maintains the assumption that electrons orbit the nucleus in circular orbits. However, a key improvement here is that these electrons are in fixed, so in other words, quantized orbits. These orbits are basically analogous to electron energy levels in the atom. We learned about such energy levels earlier in this topic. Since orbits are quantized, electrons cannot gradually move from one orbit to another. Instead, they need to absorb or emit a quantum, or in other words, a package of energy, in the form of a photon. Similarly to what we learn about atomic energy levels, the absorbed or emitted photon must carry a very specific amount of energy. A third assumption of this model is that the angular momentum of the electrons in these orbits is quantized. As opposed to the Rutherford model, in these orbits, electrons do not emit electromagnetic radiation, hence they do not lose energy. At the time, this was a revolutionary idea. The formula to calculate the angular momentum of an electron in a specific orbit looks like this. We'll also add the list of the variables. If you think back to what we learned in subtopic 8.4, you might recognize that mvr on the left-hand side of this equation is angular momentum. Now, as on the right-hand side n is an integer, in other words a whole number, this formula shows us that the angular momentum of an electron in an atom is always an integer multiple of h over 2 pi. Since h over 2 pi is a constant, angular momentum will always be an integer multiple of a constant, which put differently means that angular momentum is quantized. The second equation that Bohr developed based on his model is also provided in the data booklet. In this formula, E is the total energy of the electron in the nth energy state, or in other words, in the nth orbit, and n is the number of the energy state, with n equals 1 representing the ground state, n equals 2 the first excited state, and so on. Let's add that EV at the end of this formula shows that the given energy value is in electron volts and not in joules. As we saw earlier when learning about energy levels, the energy of an electron that is bound to an atom is negative. A final point before we move on to a bit of algebra work is that one of the main shortcomings of the Bohr model is that it only works for simple hydrogen-like atoms. When extended to more complicated atoms, the model fails. And now onto some algebra. The derivation of the first formula requires the de Broglie wavelength equation, so here we won't go into this derivation, especially that it is unlikely to come up on final exams. We will, however, take a look at how the second